The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Well, let's see if we can't get started. Everyone, I trust, can hear me adequately. Welcome back. It's Tuesday. For those of you who are not in my recitation section, I'm Dave Gossard, and I'll be your lecturer for the day. Professor Vandiver is out of town. It looks like some of you may be as well. We probably could have held this at the gate at Logan Airport and got done a little better, but be that as it may, I'm glad you came. This should be fun. Today we have a new topic and a demonstration, a real physical system. So unless there are any outstanding questions, anybody have any questions or complaints to address to Vicente? No. All right. Hearing none, let's go ahead and get started then. Today, the topic is multiple degree of freedom systems. Now, to date, with a couple of exceptions, all of the systems that you've dealt with had a single degree of freedom, either a linear displacement x or an angular displacement theta. You know what the concept of equations of motion, or I should say the equation of motion, and the notion of undamped natural frequency. Today we're going to generalize, if you will, to systems that have not one but multiple degrees of freedom. And see how those notions generalize. All right. In particular, as you might expect, the system that has multiple degrees of freedom has multiple natural frequencies, also known as eigenvalues, as we will explain here shortly. Multiple degrees of freedom systems have a new property, a new characteristic you haven't seen before, and that's what this lecture is all about, is to illustrate that to you and demonstrate it. It's the notion of natural modes, also called eigenvectors, and then the general response to initial conditions. So that is the plan for the day, and we'll start with this. This is kind of a classic textbook case, two springs, two masses, straightforward extrapolation of what you've done before. You got a spring K1, mass M1, spring K2, mass M2, and the displacements are indicated as shown there. X1 and X2. I want to hasten to point out that the displacements we speak of here are defined with respect to the static equilibrium position. This is a notion that Professor Vandiver went over at least once, and for those of you who've forgotten it or weren't there that day, I have, for your reference, essentially reprised that notion over there. But so in the meantime, let me press on. If you have any questions, we can go back and cover that. But assuming you agree, let me simply say you got two springs, two masses. The typical way we've taught you to do it is if you're going to generate the equations of motion by the direct method, you generate two free body diagrams, some forces in the X direction for each of the masses, get F equals ma, and you'd get these. Conversely, you could also do it by Lagrange. You could generate the expression for the kinetic energy, for the potential energy, form the Lagrangian, do the Lagrange equation business, and you'd get the same thing. But either way you do it, what comes out the other side looks like this. And it's not a bad exercise for you to, offline, convince yourself that this is right. Not right now, but in the comfort and leisure of another time. AQX1, I do X2. All right, so there you have it. That's what the two equations of motion would look like. Again, either by the direct method or by Lagrange, you end up in the same place, so to speak. And now for today, we haven't asked you to do this much, but let me simply say the weapon of choice for multiple degrees of freedom system, because there's a certain repetitive quality to it, matrix notation is preferred. And these equations over here, written in matrix form, would look like this. All right. And it looks like this. There's two matrices, and let me hasten to point out that this is exactly this and nothing more. There's no magic, no additional derivation. This is simply a restructuring, a reorganization of these equations. And if this may seem foreign to those of you who have not had any or very much linear algebra, do not be dismayed. It is not a difficult thing to learn. As you know, a matrix, as you probably know, a matrix multiplied by a vector, or multiplying a vector by a matrix, is done with two hands. The first item is, for example, is m1 x1 dot plus 0. That gives you this term right here. All right, over here you get x1 times k1 plus k2. That's this one. All right, and here you have minus k2 x2. That's that term. All right, so matrix notation, this becomes that, no problem. It's like a model train set. It's great. Everyone should have one of these. All right, what I would like to do for our example here is because we're going to be doing some algebra for the express purpose of simplifying the algebra, let me consider a special case where where the masses are identical, and we can simply call them M, and similarly the springs are identical, and we'll simply call them K. At that point, these equations become simplified. Excuse me, that's just M, that's just M. Okay, very good. So this is the problem we're going to work this. We're going to tackle this problem first because it's, as I say, it simplifies the algebra. Now here is, this is not an assumption. This is a I would call this more a mechanism to get this job done here. Harmonic motion is one where we assume that the masses oscillate at the same frequency. So what this looks like is this. What we're basically saying is that x1 is actually equal, x1 has amplitude A, I'm being attacked here by the second board. All right. Basically, the situation here is that we're assuming that both of these masses move. They don't move exact. I wouldn't call it exactly together. They're not in complete synchrony, as you'll see here in a moment. But what they are is they're going through a sinusoidal motion, and it is an oscillation at the same frequency. Both of them are oscillating at the same frequency. All righty? However, they differ in their magnitudes. They are not the same magnitude. All right, so, but that assumption right there allows us to say this. If we differentiate those twice, we get the following. Okay, that comes back out. Douglas, where's that minus sign come from? Can everybody read that? You guys read that in the back row here, Steve? It says that, for example, this says that x1 double dot, if x1 is a1 cosine, then x1 double dot is a1 cosine preceded by a minus omega squared. Where does that come from?
The minus sign came from when you differentiated the cosine the first time.
Exactly. And the cosine returns, and that's what you get. Well, here is, shall we say, the heart of the matter. When you substitute this into this, let me call this, not to get too obsessive over this, but this is our equations. These are our equations of motion. So when we you get this. Equals 0. Excuse me. Many people, I think, simply put a big 0 there, but to do it properly, it's 2 zeros, if you will. And again, forgive me for writing this out, but I would like you to be able to do this by yourself to recreate this after the fact. Okay, this becomes dividing and collecting terms. Okay. Anybody unclear about how this is obtained? Yes, ma'am. Emma.
I can ask a question about the previous one.
Yeah?
In the second term on the left-hand side, should it also be multiplied by A1, A2?
Yes, it should. Thank you very much. Oh, hey, oh, hang on. Yes, thank you. That's exactly right.
Also, the off-diagonal terms in the lower equation?
Hang on a second. Should you get for fighting the boards here? Let's just see, one thing at a time. I got A1, A2, cosine by t minus phi equals, okay, now Emma, does that take care of you? Yeah, and you said, Vicente?
The off-diagonal terms, shouldn't they be a minus?
I'm sorry, that's absolutely correct. Wonderful. All right. All righty. So there we have it. Any other questions? I hope I got it right. Yes, sir.
Are they plus K?
I'm sorry?
Are they plus K?
Plus K. No, they're minus. Yeah. Why is that? Do I see that? This is a straight. There's less here than meets the eye. This is a straight aggregation, collecting of terms. All righty. The minus got added to the mass, to the elements of the mass matrix, but not to the K matrix. The K matrix goes through as is. Okay. Now the question on the floor is, what do we do with this? Can everybody appreciate that, kind of get out of the spring mass business and kind of look at this from a math point of view. Does everyone appreciate that this is a set of linear equations? There's a, you know, the old AX equal B kind of thing. And if you recall, to solve this, what we're basically going to do is solve for A1 and A2. That's the game we're playing here. All righty? And if you recall from your math course, the determinant of this has got to equal 0. All righty? So let me simply repeat it here. The determinant of has got to equal 0. All right, and you recall the determinant is for at least a 2 by 2, you can do it by hand more or less. It's the cross products with appropriate sign. And I'm sparing you some algebra here, but trust me, when you do this, this is what you get. All righty, m squared omega 4 minus 3km omega squared, okay, plus k2, that's it right there. This little guy, sorry, I can't do that anymore. I know, it's this one. That is called the characteristic equation. All right. So here's the first answer. Yeah.
What is K2? Should that be K squared?
I'm sorry, that's a typo in my, that's simply K. Or K squared rather, sorry. Thank you. Thank you.
I think in the above line, the determinant, the upper left should have a 2K.
Oh, this is 2K, yeah, absolutely. All right, 2K, good enough? All right, thank you. All right, so let's send this to the top. Okay, so the roots of the characteristic are the natural frequencies, all right? Let's do this way. All righty? So, did I do that right? Yeah, plus or minus. So, situation is that when you apply the quadratic formula to that characteristic equation to find the values of omega for which that equation is satisfied, those omegas that come out are the natural frequencies. They are the quantities we seek, and what that yields, as you can see from the plus or minus here, there are two of them. Well, I'll write the whole thing out here. And these are numerically okay. Everybody see that? So here are our two natural frequencies. Here's the first one. Excuse me, that's not right either. That's the square. Okay, so these are our natural frequencies. Once again, for this special case where the masses are equal and the springs are equal. Anybody recognize that number, 0.618, for all you fuss budgets? Ring any bells? Any number freaks here? No? I heard it. That's it. Exactly. Nice job. The golden mean, the golden ratio. Also, let me simply say, if there are, as far as the number of things, if there are n degrees of freedom, there are n natural frequencies. Okay. Let me see. What else? Yes. All righty. So that's that. Okay. So now it's time to get to this notion of the natural modes. Let me say we got to go all the way back to this set over here. If you take the first row of this matrix equation, that's the first of the degree of the equations of motion, and you make that assumption of the harmonic motion in there. Okay? Okay, does everybody see that? What we've done is we've taken basically the first row of that expression right up there and formed the amplitude ratio A1 over A2. What we're doing is we found the omegas. You remember, just to review the bidding, our original assumption was harmonic motion. That is to say, all the displacements are moving in synchrony, as it were, the same sinusoidal frequency. We've just found what frequencies those are. There are two of them, and they're right there. Okay, now we're after these guys. Now we're after the relative magnitudes or the relative amplitudes of A1 and A2. And we, from one of the equations, isolated one of those. And let me just say, if you plug these back in, plug in the first one, you'll get oddly enough, .618. Okay, these amplitude ratios are the so-called natural modes, all right? And I think you can appreciate that this is the first one, and this is the second one. Okay, now over here. Any questions so far? Wonderful. Hearing none? Yes, ma'am. Sarah. You see this amplitude ratio, you saw how we got that. You see that the right-hand side has got system parameter, K's and M's and stuff like that. But this is the ringer, you know, omega. This amplitude ratio is expressed in part in terms of omega. So what omega, there's no ambiguity as to K's and M's, but what omega? Well, the answer is when we plug in this one, you get this answer. When you plug in this one, you get this answer. So, while we're at it, Sarah, I hazard a guess. How many natural modes do you think we got? Yeah, exactly. Okay, so you're going to have one of these for each degree of freedom. Okay. Let me just point out a couple of elements here, and then I'll show you a demonstration because we have to have some fun today. These are point of information. They're ratios, not absolute magnitudes. Okay, that's number one. The second is, I already told you, they got the same number. Okay, each natural mode is associated with a particular natural frequency. Okay, this one goes with that one, this one goes with that one. All righty, and once again, they're associated with, Yeah, let me say that. I need another board. Let's just go over here. So, in a sense, this is decouple. All right, to decouple into, essentially into independent subsystems. Okay. All right, so in general, what the system's response looks like is I'm talking about the one in front of us here, this special case where the masses are of equal, the masses and springs are equal. I think there's a minus sign in here. Just come up. Wonderful. right. That's it. Everybody see that? Yes, sir. I'm sorry?
What does it say on that first bullet point?
Here? These describe the situation in which the entire system is oscillating at wait a minute. It's the second board here. Thank you. Okay?
At what?
At one frequency. Sorry, I'm just getting a little tired of writing. Okay. So, any other questions? Problems? Complaints? All right. Yes, sir.
Why is one of the, you have 0.618 in one, and the other one is 1.618 in minus one?
That's correct. Oh, then, let's see. Then there's a mistake right here. Thank you. Yeah, because that's the way it came out. All right, when you plug omega 2, having this value into here, the amplitude ratio comes out minus. All right? Fair enough? Now, it threw me there for a minute. I thought you were going to say, why is the minus sign there? Rather than, you could have had minus 1.618 and plus 1, right? And the answer is no reason. Because these are ratios. Yeah, Caitlin?
But shouldn't, like, when we go back and look at our, what you wrote down as 3 plus radical 5 over 2, how, I don't understand how that would.
I'm sorry, say it again? Find it? Yeah, I mean, they're ratios. It's just simple as that. So you multiply them by any number and it still works. Well, I'll actually show you here in a second. At least I believe that's the case. We'll just see here in a second. Okay, questions, comments? All right. Now's the time. Can I bring up the sideboard here? Okay, let me show you. Anybody here taken 2086? Wonderful. Yeah, one person? Great. Okay. Anyway, I believe in 2086, don't they teach you MATLAB? Isn't that the weapon of choice? Okay. That's the program I'm using here, MATLAB. For those of you who haven't seen it yet, it is definitely a mixed bag. I don't know how you feel about it. It's very, it's very powerful. It stands for Matrix Laboratory. It was written, 20, 30 years ago here, I believe, at MIT, by people who are into matrices, into matrix algebra, okay? And it's kind of command line oriented. Good news, it's very powerful. Whatever you want to do, you can do in MATLAB. The bad news is the user interface stinks. The language is very difficult to learn. It's even harder to remember. So with that rousing endorsement, let me show you what we've got here. This is a program. Is that font readable by you guys? No? No? I'm sorry?
I think if you didn't forget your address, it's fine.
Yes, well, I believe I can, here we go, fonts. There's upping the fonts is a kind of a mixed bag because you get bigger letters, but they're, okay, how's that? All righty, so here's the situation. This is a MATLAB program, and I'll explain to you what it does as we go. See if my little cursor is here, but I can't see it. All right, here's the system parameters. Once again, we're doing this simple spring mass, this simplified spring mass system, exactly the one we've done here. I've called it only, when I wrote it, I generalized, you'll see, I generalized it to do this guy. So we got M1 and M2, K1, K2, but if you'll notice, you see here, their values are equal. We got the mass at 1 kilogram each, and we got 10 newtons per meter on each of the springs. All right? Everybody appreciate that this system's numbers that we're putting in here match our case here, K over M. Okay, and you can see here we've defined, and again, you're not, let me just say, I'm not trying to sell you on MATLAB, and I don't want to leave you with the impression that we expect you to be able to instantly become a user of MATLAB. This is simply to illustrate the point, the point of the lecture here. Here is the M, the system matrix, there's the K matrix, and I'll show you the eigenvalue and eigenvector thing later. But let me take my word for it. See this here, ODE 45 is a cryptic allusion to the Runge-Kutta algorithm, fourth order Runge-Kutta, that is the kind of workhorse for integrating differential equations. And so why don't we just, let me just run this. And what I've got here is, here's the point I wanted you to get here. If I get, because I'll bet you can't see that cursor either. Yes, anyway, you see this right here? T-span is the time scale and the time step defined up here, but these are basically the initial conditions. See it here? X1, X1 dot, X2, X2 dot. So here's the first one. Okay, this is a 0.618 is for the X1 and 1 is for X dot, or excuse me, for X2. Everybody appreciate that? Got it? Okay. How about it? OVA, what if these are the initial conditions, what I've done, I have artfully chosen the initial conditions to have the same ratio. What do you expect is going to happen? When I turn this thing, I got a simulation here. I'm going to run this, and you're actually going to see it. What do you think you're going to see? I got it's two spring, two mass system. What I've done is I've displaced the two masses. They'll certainly have that amplitude because I'm putting it in there, right? That's the initial condition, right? All right. Question is, what frequency do you think they'll oscillate at? Pardon? Yeah, they will certainly. Each of them will oscillate with the same frequency for sure. But what do you think it's going to be? It's going to be that one. All righty. So off we go. So let us hope that yours truly's program worked. Okay. Here we go. Boom. Oh, look at that. OVA, please interpret that for me. What do you see there? Hang on a second. Let me blow it up so you can see it. Ooh, isn't it pretty? Okay. And the green, excuse me, I believe the blue is X1, and the green is X2. See? Okay, everybody agree? Everybody appreciate what's going on? You pull them both at the slightly different, you basically used the first natural mode as the initial condition, and sure enough, they oscillate together. They oscillate at the same frequency, they oscillate at that frequency. Let me just see, I just want to make sure we get the full value out of this thing. I computed, well, of course you can't see it anymore because our numbers are so big. Well, that's great. Anyway, take my word for it that, oh, here it is. The period for the first natural frequency, or I guess it's the second, it should be like 1.2. Or is it 3? Yeah, no, I'm sorry. The period is 3.2. And sure enough, there it is. It's about 3. 3.2. Fabulous. Everybody got it? Okay, now watch closely. Let me see if I can do this. This requires a little dexterity, which is always a short supply here. I have to hit this. and this. Make sense? That's what it actually looks like, okay? They're both oscillating at the same natural frequency, going up and down together, but they have different amplitudes, okay? So one's bigger than the other. So that's what it looks like. Questions? Christina, you get it? Clear enough? Wonderful. Okay, so let's go to our program, and instead of that set of initial conditions, we'll do the other. Ovier, read them to us here. What are the initial conditions here?
It's 1.618.
That's right. It's this guy. It's this guy, okay? It's this ratio. It's this ratio. So I basically arbitrarily chose, is it negative first? No. I chose, I chose that one over there, 1.168, or 1.618, and then a -1 for the second one. Fair enough? Okay, there it goes. We got to save it, make sure we got it. So you got a clue what's going to happen here? Okay, here we go. Boom. Ooh. Look at that. Ovier, what's going on there? Yikes. Explain me. What is that, good, bad, indifferent? Is it right, wrong?
The way the system acts, it has a higher frequency.
Yeah, exactly. First, two things. One is they're out of phase. They're doing this. Okay, one's going this way and the other's going the other at different amplitudes, but the same frequency, but the frequency in question is higher than the previous.
Why are they out of phase?
I'm sorry?
Like, why are they opposite of each other?
Ovier, why are they opposite each other? Because we made them that way. We said that's the initial condition. Does that make sense? That minus sign does it. Okay, one starts this out and one starts in, and they do that. Clear enough? Okay, now what's going to happen if we just choose any old initial condition? These are special. We worked like a dog to compute these, okay, so that the system would decouple in that way. So what if we, now, let me put that back. Now look at this one. All right, look at that. One and, read that to me. Yeah, so it says the displacement, the initial condition for the first mass is 1, and whatever that is, the second mass's initial condition is half that, in same direction, both positive. So, Christina, they're going to go together, whatever, yeah. But, Ovier, at what frequency? Any idea what it's going to look like? If you do, you're a better man than I, okay? Because what you're going to see here is that. It's this thing right here, okay? It's that expression right there. And here's what it looks like. Let's see, did I stop the? Oh, wait a minute. Did I ever show you that before? Oh, I didn't. I think I forgot to show you the other. Anyway, not to worry. Hang on a second. I got to stop this guy. First, I have to find my figure. Oh, there it goes. That's the previous case. Okay, when they're out of phase, different magnitudes, but going in opposite directions, and you can see they're going at a higher frequency than before. Make sense? Okay. So now we are, just to refresh your memory, now we're going for the third case in which there's nothing special. We just picked a couple of initial conditions out of the hat. And here we go. Oops, I think not. I think that's the previous case. So let's go here. This is another wonderful thing about MATLAB is nothing happens until you save it. So we were just running the previous case. Ooh, nasty. Look at this. All right, can everybody see that? This is simply, if you can interpret this, you're smarter than I am. But what this is simply this expression over here. Okay, it's this expression for just some arbitrary initial condition. Do you see that behavior though? Each of them, they're going together kind of, but they, anyway, watch this. Here's what the simulation of that looks like. All right. What the heck is that? All right. Well, anyway, the point of the story is that multiple degrees of freedom system in general's response can be arbitrarily complicated. It's not arbitrarily complicated, but pretty complicated. You'll get, in general, if it's an nth order system, if you don't know anything about the worst case, you'll see 4 frequencies in there. All right. And they're all mixed together in some mystical way that's unknown to you. Fair enough? And it's only when you reach the natural modes that you actually find out what is going on here. All right, well now I have to turn your attention to this guy. All right, this is made by Professor Vandiver's machinist. A perfect example of a second order system. And I bring it to your attention here for 2 things. At the end of the day, what we're going to do is I'm going to demonstrate exactly what I just did for the kind of textbook case, the textbook system. I want to demonstrate exactly this, exactly the same thing for this guy. Only this is a real system. Alrighty, very nice. We have a steel rod that must be 1/2 inch in diameter. The whole thing weighs several pounds. These sliding masses are right circular cylinders with a hole drilled through them. It's ever so slightly larger than these here. They're of different lengths. They're made of brass. They're serious masses. And the springs, which extend from here to here and from here to here, are wound on a lathe and attached and so forth. Pretty, no? Okay, very nice. Well, now look right off the bat. Did you see how that thing operates? Would you agree you have some complicated behavior here? All right, now you would also, would you agree that this is like that? Everybody see that? Let me, before we go too far, this is a mixed message here. Jai, is this exactly like that? In what way is it not? Or in what way is it similar to that? Well, what is clear is that you got 2 springs and you got 2 masses. Okay, about that there's very little argument. It's damped. Can everybody see that? How does Jai know that it's damped? How does he know it's damped? I mean, that's just a wild guess on his part, but. And it slows down. This is the most important part, is that it stops. Okay? Eventually, if you come back in a minute or 2, it's done. All right, Jai, you're on a roll. There's definitely damping there. What kind of damping? Friction. Friction, yeah. Does that have a name? Does it have another name? Do you think of? It's definitely friction. It's not, what it's not is viscous friction. What it is not is a damper or a dash pot of which we've shown you before with the ideal expression that generate a force that opposes the velocity, generates an opposing force that's linearly proportional to the velocity. What's going on here, you think? What kind of damping do you think? It's called Coulomb. This is called Coulomb damping. And this is a digression. Now we're on the part where this is really, everything that's on the board is what I want you to really come away from today with. So now we're out kind of in the, I would call it the winging it area right here. Because this is the part where, where I simply had fun with the demo. Okay, this is viscous. And this has got the symbol, well anyway, this is what it looks like, and this is the force of the damper, I'll call it B, and this is the velocity, and this is the constant of proportionality B, and it has this little symbol like that. And when equations of motion are solved that contain that, the response looks like this. Okay, what we're talking about here okay, the force put out is a constant. And that just comes from the sliding, all righty? And what it generates are distinctly nonlinear equations of motion. And what you get here is you get this kind of behavior. If you really looked at it, what you'll see is there's definitely damping for large motions when the forces, inertial forces and so forth are large compared to the friction forces. It'll look a lot like conventional viscous damping. It's just that when motions get really small and the forces get down there to on the order of this, all of a sudden you'll see on one cycle it'll just stop, okay? And were you up here where you could see, if we had a close-up of this, you can't see it, but no, you just watch this thing stop. Right there, do you see that? That's a little hard for you to see from there, but watch. Right. Anyway, were you up here, you'd see this. That's what we're looking at. All right. Well, here we go. I need some help here. Who's in a volunteering frame of mind? Hey, Amy. All right. Good. Glad to appreciate the help here. Here's what I want to do. We just blew out some wonderful theory. Okay. All this is just solid as a rock. Yes, sir.
For the Coulomb friction, is that a linear fall or is it still exponential?
I'm sorry? Oh, no, it's not. I'm sorry. No, if I'm not mistaken, I really didn't look this up, but I believe it's linear. I'd have to, take that with a grain of salt, but I believe it's linear. Yes, Amy, here's the situation. We have all this marvelous theory. My goal is to, and we have this fabulous demo apparatus, though inherited. And what I'd like to do, we have computational means to, and in fact, we just went through the exercise. We already know those same equations that work for this, because they're general. However, it's not my piece of apparatus, and well, here's the deal. What are the M's and K's? What are the values of M1? I need M1, K1, M2, K2 to put into the...
From that apparatus?
Yeah, that's what that's what I'd like to do, is I'd like to...
Do I have to just determine them by looking at
Oh, no.
I'm not that
Yeah, no, you're my assistant. I guess the question is, how would you? This is the, and I got to tell you, that's the math part of the program. Now we're in the engineering part of the program, okay? Because somebody gave you a real live demo apparatus, works like crazy, or appears to, and I'd love to take advantage of it, but I don't know any of the numbers. No. Okay, that's the constraint I'm operating on. It doesn't belong to me. I mean, I could take it apart, but that's an absolutely appropriate thing to do. I would have liked to. It'd be easier if you could. You just go, yeah, take a screwdriver to it. Here, put this on there, and pull this on. I didn't have a luxury of any of that. So, what's your next best suggestion? Nice suggestion, but no secret. I'm sorry. Well, yeah, no, that's fudging. Yeah, they notice. Have you ever taken apart anything made in modern manufacturing method? Oh, it's good, because you can't put them back together. Okay, they're assembled by machine, and once upon a time you could disassemble and reassemble things without detection, but anymore, once you take them apart, it's wicked hard to get them back together. Okay, the floor is open. I need another suggestion. What are you going to do?
Do you need to know like the exact K&M, or do you just need another ratio?
I thought you were going to say, I need to know M or K. I need to know them all.
Do you know the density of the?
Oh, what I was going to say, but I don't need to know anything exactly. Okay, all I need to know is as good a guess as you can come up with. It's all an estimate.
If you know the density of the material, you can easily work out the weight, because I'm assuming I'm allowed a ruler.
Oh, absolutely.
The dimensions of the masses.
Wonderful. Okay.
You get the density.
Absolutely. She hit the jackpot, rang the magic buzzer. That's exactly what I did. Okay, here's a little crummy sketch of the, oh, you can't see that. Anyway, these are right circular cylinders with holes in them, and they got measurements beside them. I can tell you this is 75 millimeters, this is 35 millimeters. This one is 37 millimeters long, and blah, 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 blah. All right, so I did that. That's great. That's an excellent suggestion. And after, I did exactly that. I won't write out the formula. You know area and volume and all that. This is, let me get you in the right order here. M1 is 0.2929. And M2 is 0.5938. Okay, everybody got that? This was obtained by taking a ruler to these things, taking diameters, lengths, and diameters of holes, multiplying them times the density of brass taken out of the book. All right? Do you believe that? Or excuse me, do you believe that number? Well, you're a better man, you're a trusting soul. I don't. Okay, to me, I believe that number. Yeah. Okay, this is done with a ruler. All right, the little millimeter thingies. Okay, so I just say don't fall in the trap of false precision. Anyway, okay, Amy, you're on a roll. We got the masses. What now?
Free body diagram.
Yeah, well, we got all that. We got a.
You've got that, but then what you can do for the spring, the forces of the spring, when static, don't move it.
Yeah.
Don't move it right now. So take the top mass. It's not moving, which means that you know that the force going upwards, which is the spring,
Right.
is equal to the force going downwards, which is
Nice.
So you can measure the displacement from the start of the spring to the bottom of the spring. Do you know the natural length of the spring?
No. Okay. Anyway, what I was going to say is, excellent idea, can't do it. Okay. But what Amy was basically saying was, well, why not simply, you know the masses now, Why not simply take from that expression right up there, okay? mg over k, right? Okay, what's the problem with that? How about it, Devin? How come I can't do that? Yeah, I really don't know the no-load position. Okay, is that it, Amy? Right there? Maybe. Why, Devin, is it, you're the one who suggested it, is that are those the no-load positions of the masses? And if not, why not? I mean, they give you a clue there. Yeah, Nick.
They can't be because there's static friction.
Exactly. So, okay, Nick, you brought it up. What's that number? You don't know that either? No. Exactly. Okay. Like I said, Amy, nice idea. No cigar. What else? We're running out of time. We're going to have to, how about any suggest? Oh, here you go, Douglas.
Could you displace each mass a certain length and then measure the time it takes for them to stop and get the damping ratio?
Get the damping ratio. Well, I'll tell you what. You want to say that again? He said displace one or both, count oscillations, and get the damping ratio. Nick?
Do we have anything like a force gauge or a spring scale?
No. This is my living room I'm talking, or my study. Anyway, Douglas said, I forgot what you said now. You said, oh, I know. You said displace it and count the oscillations, get the damping ratio. First off, the damping ratio is no help, okay, even if we did get it. And the only formula for which we've ever given you, the only formula we've ever given you to do that with pertains to this kind of friction, which is not present. No cigar. Nick says, how about force gauge? No, don't have it.
Well, if you assume that the damping is small, then
Yeah, we are.
you could hold the first one steady, displace the other one, and then find the frequency.
What's your name? Sean or John? Sean, yeah. Say that out loud. Say it loud enough that Devin can hear you.
So you hold the first mass, and then you displace the second one. And
Like this. Oh, hang on. He says, hold the first mass, like this set screw right here. And
then displace the other one. And then,
like that. Actually, to answer your question, Nick, the only instrument I have is a clock. Hang on a second. Here it is. Of course, this is the big task, is finding it. Okay? Count to 10. Remember, like Vandiver told you, skip 1, 1, 2, 3, count to 10, stop. Excellent, excellent, excellent. When you do that, excuse me, that's the second one. Well, I did that, and right here, it's TP, the period of 10 of those, or excuse me, 10 of them, then I divide to get 1 is 0.83 seconds. Okay, what does that tell you, Sean? Well, actually, these two, yeah, you can get the frequency. What this does, you can because this gives you the frequency. You know, in general, that in particular, you know that the second natural frequency, which is just associated with this single spring in a mass here, it's just this guy. Okay, it's not both of them. Anyway, this turns out to, I didn't graph that. That's square root of k over m. Trust me, you can put those two together and you get K2 is equal to Newton meters. Okay? This is exactly what you said. Okay? Freeze the first mass, displace the second, use the measure the period, you get the natural frequency for basically K2 over M2, K2 over M2, right? So you got K2 out of it. Yeah, Douglas?
So how come it gives you just a natural frequency and not a damped natural frequency because of the?
Oh, no, it absolutely is. It's all damped. Yeah, no question about it. Okay, but again, what we're doing is we're going close enough, all right, because I have nothing. All right, so even the damped natural frequency is better than nothing. All right, so Amy, back to you. You're back in business. What now? So now we've got M2 and K2.
We just need K1.
Yeah, now we need K1. What do we do now?
And we can't do the same thing that we just did for K2 because we've got the spring on the bottom. You've got two springs.
Exactly. Well, not quite. Well, let's see. Now I'm going to turn loose. Oh, so now we're back to our original system. Okay? It doesn't hurt anything. It's just ugly to look at. Now what? Sean, you want to do that trick again? Push this one up. I don't think so. Yeah, Nick.
So just fix the second mass.
Fix the second mass.
The screen, the total, so you solve for the,
Yeah, you see this frequency here? Yeah, Chandler, I'm going to overrule Chandler. I'm going to say this is the natural frequency of that mass and these two springs. Okay, do that same trick again. You get the equivalent spring rate, subtract the second from it, and you get the other one. Devin, is that what you're going to say? Wonderful. That is exactly what I did, and you get out of it, you get K1 is equal to 50.45. Okay, Newton per meter. Okay, in the interest of time, I'm going to short circuit this. I took exactly these parameters, I ran them, I put them into that same computer program we had before, and what came out, I have to have a place to put it. Ah, wonderful. Okay. And now I have to find it. Here we go. And here are the two modes. Actually, let me put it right here. Okay, for this system, okay, yeah, because here's the first one. And here's the second one. 0.9760 and minus 0.2177. Everybody appreciate that? This is the same, by the same computational procedure we spoke of earlier. And sparing no expense, we have here a fresh from my basement, custom-made initial conditions setting device. I can hopefully avoid killing myself with. Okay, here's what we have. So, I guess I didn't show you this first. If you can see it, what we have marked is the reference position. That's the rest position that we couldn't find by laying it down. Or excuse me, this is the reference position when this is the static equilibrium position of mass number 1, static equilibrium position of mass number 2. Mode 1 over there, 0.4, what they said over there, 0.497 is down here. Mode 2 is over here. All right, so Devin, while I'm doing this, tell me, how am I going to know if this is right? If this is all just bogus? What observable is going to tell me that I got it right? I'm sorry, speak up. How about it, Nick? Exactly. And you ought to be able to see it from where you are. All right? Can you appreciate that they're not at the moment? All right. Now, hang on. Okay, here comes mode number 1. This takes 2 hands to do it. All right, you ready? This is mode number 1. Again, it's those numbers. How about it? Can you see it? Very good. How about the other? And so here, this is number 2. And this is a little more complicated because the other one has to be done from the bottom. Hang on a second. All right. Now this one, what we're doing is we're deflecting. This one is positive, downward, okay, so X1 is down, but X2 is negative, so it's displaced upward a bit. Are you ready? Would you expect, Nick, do you expect this, what do you expect to see this time?
So the frequency should be higher and they'll move in opposite.
That's the key, okay? Is they're once again, they're going to move at the same frequency, albeit in different directions, but that new frequency is going to be higher than before. And sure enough, stand back. Okay, so there you go. What did that tell us? That told us that to first order, we got the system parameters identified correctly, and the theory holds up. Questions? Comments? Complaints? Devin? I'm sorry? The second set of initial conditions were right here. This is the second mode. X1, 0.97. X2, minus 2.2. Okay, have a great Thanksgiving holiday.